All right, let's talk about buffers. The definition of a buffer is that of a solution that contains a conjugate acid along with its conjugate base. But in addition to having both of the conjugate pairs in the same solution, they both need to be weak. That is the definition of a buffer. So when you think about the substances you're dealing with, it's very important that you remember the list of strong acids that I mentioned in the previous lecture. There's 11 strong acids that you have to remember as being strong. And the reason why is because any other acidic substance will be regarded as being weak. And you need to use that in order to determine whether you're dealing with a buffer or not. Alright, so everything else, these are your weak acids. Oh, and by the way, if you have a substance that happens to be a base, but you only have pK values for the conjugate acid, you could use the following relationship right here, 14 equals pK plus pKb, to derive the pKb value of the base. Right, so each one of these substances can have its pKb derived, and of course that pKb value will not correspond to the substance written here, but rather to the conjugate the conjugate base of those substances. All right, now pKb value is some idea. If you have the Kb value, you can find the pKb, and using the same formula, you can find the pKa of the corresponding conjugate acid of the substance. So we're going to make use of that, rule to try to find out what we're dealing with. All right, now going back to the definition of buffers, you want to have in your solution both the conjugate acid and the conjugate base present, but they both need to be weak. Which, by the way, when you look at water is a weak acid or a weak base, depending on how it's reacting. In this case, it's reacting like a base. It's a weak base, but the conjugate acid of water is in fact a strong acid, so this will not correspond to a buffer. In fact, you never refer to water as being a buffer solution because water by itself does not meet the qualification, does not meet the criteria to be a buffer. Another thing I want to point out right now, this is going to be more important in the next set of lectures, but the buffer region, when you look at this titration curve, the buffer region appears right at the onset of the curve. It happens right before this inflection point where the slope of the line kind of shoots up really steeply. So right here in this kind of like moderate region, this is where the buffers will actually coexist together to give you, pH for your solution. I'll show you how to calculate those things in a little bit later. The same thing applies to the base association equation and its graph. The buffer solution is always at the beginning before you hit the steep line that appears in the middle. Alright, so those are your two buffer regions. This is for the weak base counterpart, this is for the weak acid counterpart. But regardless, it happens right before you hit that inflection point. And the other thing too that you may notice by looking at the graph is the fact that the pH is not changing all that much. It is changing, granted, a little bit, but it's not changing by a whole lot. And so what the buffers are ultimately doing is they're minimizing the changes in pH. These titration curves are basically representing addition of extra acid to it or extra base, and the pHs are changing in that respect, but they're changing very little. So the buffer solution that needs to be made up of a conjugate acid, a weak conjugate acid, and a weak conjugate base ultimately allows the solution to fight drastic changes in pH. So it basically can regulate the pH of an entire system, and in essence, our own bodies do that. We have substances in our bodies like hydrogen carbonate that serve as buffers for a system. And it's important that our pH remains relatively balanced and constant because a lot of the enzymatic processes that allow us to survive and continue living depend on constant pH and constant temperature values. So if you have a high fever, that's bad news for you. If your pH gets messed up, that's also bad news for you because you will mess up the enzymatic processes that you require to breathe. And if you can't breathe, you're gone. So this is an important factor that plays a role that goes beyond chemistry. You see it in biology quite a bit. All right, now what we're going to do is we're actually going to do some calculations involving these buffers. I'm going to start with an ice table approach, and then I'm going to show you a different approach to solving the same type of problem. So in this example, I have acetic acid dissolving in water, creating hydronium and acetate, the conjugate base of acetic acid. What I'm saying in the problem is that there is an initial concentration of acetic acid and acetate to begin with, 1.5 times 10 to the negative 2 for acetic acid and 1.0 times 10 to the negative 2 for acetate. You have to have both of those things present, otherwise you don't have a buffer. The Ka is also given, meaning that we have to write specifically the acid dissociation equation. So start with acid reacting with water, yielding hydronium and conjugate base. And like anything else involving acids and bases, we're after the pH. So the ice table will have the one reactant other than water. It will have the two products. Initial concentrations, we have the data for acetic acid and acetate. Nothing has been said about hydronium, so we assume it to be 0 to begin with. And the change in concentration will be minus X for the reactant plus X for either of the products. And when you add the two rows, you're going to have the following changes in concentration leading to the equilibrium concentration of this particular solution. Now, applying the equilibrium constant expression, we're going to have X multiplied by 10 to the second plus X divided by 1.5 times 10 to the negative second minus X, right? That's what this whole thing is all about. But if you divide 10 to the negative 2 by 10 to the negative 5, you're going to get a value that is greater than 400 in either case. So the minus X and the plus X can actually be disregarded altogether. And so you end up with simply X times 10 to the negative second divided by 1.5 times 10 to the negative second, which ultimately, yes, and here I'm showing you that the actual value is greater than 400, right? So 568. So once you solve for your X values, multiply by 1.5 times 10 to the negative 2 divided by 10 to the negative 2, you're going to find out that X equals 2.64 times 10 to the negative 5. And if you input those values into the table, you now have the concentration of hydronium. Quite simply put, the value of X was the value of the hydronium concentration. So now we can take the negative log of this value to find out that the pH is 4.58. And so applying the ice table to the initial concentrations of the conjugate acid and conjugate base allows us to get to the pH of the solution, 4.58. But I'm going to show you a different way of approaching this, which in some ways is more slick and more to the point. This is known as the Henderson-Hasselbalch equation, or the HH equation. And the entire premise for this is based on the fact that we're dealing with the dissociation of an acid in water, yielding conjugate base and hydronium. If you write the Ka expression for this equation, you have A minus times hydronium divided by HA. All right. Now, here's where the mathematical prowess comes in. If we take the negative log of both sides of the equilibrium expression, we're going to have the negative log of Ka, which is the pKa, and we're going to have the negative log of the entire equilibrium expression. Remembering that when multiplying things together inside the log, we can rewrite this as two separate logs that are being added together. This is the same thing as saying negative log of Ka equals negative log of A minus over HA, or base over acid, minus the log of hydronium. Negative log of Ka is pKa. Negative log of hydronium is pH. So the equation reduces to what we see right here. And now the last thing I'm going to do is I'm going to isolate for the pH. So we end up with pH equaling pKa plus the log of the base over the acid. And this equation right here, which is simply the equilibrium constant expression for the acid dissociation of HA, simply taking the negative log of both sides, this equation is what we call the Henderson-Hasselbalch equation. And I'm going to be very specific about it. This type of equation you only get to use if you have a buffer. If the solution you're dealing with is not a buffer, you cannot use this equation. So let's go back to the original example that we did, for which the pH was calculated to be 4.58 using the ice table. If we plug in the initial concentrations, and that's technically what we do, we yes, we have to find the pKa. So first we take the negative log of the Ka value and find out that it's 4.75. But here we use the Henderson-Hasselbalch equation, and we are sure that this equation can be used because we have the conjugate acid and the conjugate base present with some non-zero amount. So all you have to do is input the initial concentrations of the base and the acid into this equation. So 10 to the negative 2 over 1.5 times 10 to the negative 2. And you take the log of that, add it to 4.75, which is the pKa. And that will give you a value of 4.75 minus 0.176, which is 4.58. And that's pretty much on the ballpark, the same value, right? And so applying this formula, which technically speaking, it took me no more than maybe 2.5 steps to get it done, I got to this pretty much the same value. So this equation is actually kind of formidable in terms of finding the pH of buffer solutions. Another thing too, if you're actually looking for the equilibrium concentration of hydronium, all you need to do is take the anti-log of the pH, which is the same thing as saying raise 10 to the negative pH value, and that will give you the hydronium concentration, which is what we got by applying the ice table in the previous problem. Alright, so this is kind of how the buffers are going to play out in terms of the calculations. They're not too bad. We use the Henderson-Hasselbalch equation, and it kind of works out pretty well. Now, I'm going to show you one more feature that's also important to be recognized. That has to do a little bit with the idea of reaching the equivalence point in this titration curve. If the initial concentrations of the conjugate acid and the conjugate base are the same, something very interesting happens. First of all, you have 1.5 times 10 to the negative 2 for both of the species. You subtract X from the reactant, you add X's to the products, and you get the following equilibrium concentrations. Then, if you apply the formula, the Henderson-Hasselbalch formula, the pK is still 4.75. The initial concentration of A minus and HA are basically the same, 1.5 times 10 to the negative 2. So what ends up happening is that the ratio right here cancels out. You end up with the log of 1. And the log of 1 is simply 0. So the pH, when you have equal amounts of the conjugate acid and conjugate base, is actually directly equal to the pKa. This is a very specific point in the acid-base titrations that we're going to investigate in future lectures, but it is an important one because you can, by simply looking at the pH, determine the pKa value of your acid, and this is one of the means by which you can determine pKa values of unknown acids. Alright, so, oh yeah, and of course, take the anti-log of the pKa, so raise 10 to the negative pKa, you're going to get the Ka value as well, right? Alright, so that's everything I want to tell you for the content of this video. In the next video, we're going to look at buffer solutions, specifically the capacity of buffers, pH calculations, and the preparation of buffers. Alright, so see you in the next video.